it will, Binyam. All right, so we are in section 6.5, and let's recall now, in section 6.3 you learned about orthogonal projections, and we're seeing how important it is to find the projection of a vector onto a subspace. That's important to be able to do. And in section 6.4 you learned about the Gram-Schmidt process, where you learned how it's important to, how it's really important to create an orthogonal basis for a subspace. Okay, so these are important things. In section 6.5, we're going to talk about least squares problems. Okay, and we'll talk about what that means, but it's going to be based on an orthogonal projection. So let me give you a moment to copy down section 6.5, and then we will discuss the example. Okay, so here we have this matrix A, 3 by 2 matrix, and we have a vector B, and we're asked, does the system AX equals B have a solution X? Now, let me ask you, for the system AX equals B, this system of equations here, how many equations are there? How many equations are there? Good, 3 equations. How many unknowns are there? How many variables are there? 2. Okay, good. Is it possible to have a consistent system a system that, is it possible for a system of 3 equations with 2 unknowns to have a solution? Is it possible? Okay, so Solomon says no, it'll definitely be inconsistent. Christy says a very rare chance, maybe. Okay. Bingham thinks it is possible. So we're getting some different perspectives here. Well, okay, and only one can be right. Let me ask you this. I can tell you it is possible for a system of 3 equations with 2 unknowns to have a solution. But what would the conditions be on 2 of the equations? So it's sort of like, let's say you had something like this. Let's say, I want to be a little careful. I don't want to get too deep into it. But if 3 equations and 2 unknowns had a solution, what would that tell us about 2 of the equations? At least 2 of the equations would have to be what? Let me just, all right, maybe an example here is needed. Let's just say you had x1 plus 2x2 equals 3. And you had negative x1 plus 5x2 equals 4. And then let's say you had 4x1 plus 8x2 equals 12. Now this is separate from what we're doing here. Here's a system of 3 equations with 2 unknowns, 2 unknown variables, x1 and x2. Does that system have a solution? Okay, James says yes. Solomon says yes. Oh, why? I have 2 variables, 3 equations. I have more equations than variables. Well, is there a free variable there? I want to be a little bit careful. Maybe you're seeing something that I'm not seeing. Okay, Noah's getting where that's right, Noah. The first equation and the second equation, are they the same equation? They are. So really, I don't need this third equation, right? The third equation adds no more information about the variables than the first equation does. Okay, so let me just, I'm just gonna, what I'm gonna do is I'm gonna enter the 3 equations in here in my, one moment here. Just give me one moment, because I'm getting some different, I mean, I think people are good so far with this. Hold on here, one moment, class. One moment. what I'm doing is I'm putting the three equations in MATLAB, and I'm going to do row reduction and see what the result is. Hold on here, man. I mean, I know what the result is, but I'm just checking something because, one moment here. I'm actually doing it on my TI calculator. Okay, is there a free variable? Some students are saying that this system here, when you solve for x1 and x2, you get a free variable. But do you get a free variable? In other words, you do not. That's right, Robin. x1 equals 1. And x2 equals 1. You get a unique solution. You get a unique solution. And that's okay, that makes sense because remember, really, you have a system of three equations with two unknowns, but really, since the third equation is the same as the first equation, it's like just having two equations and two unknowns. So there's no free variable here in this situation. Okay, so the reason I'm mentioning this is, and I'm glad I did, because we had a good discussion, when like in our situation here, our system AX equals B is a system of three equations with two unknowns, but it could have a solution. You can't think just because you have more equations than unknowns that you have an inconsistent system or a free variable or anything like that. You could have a solution, and you could have it and in our case here, if two of the equations are if you have a redundant equation, you will get a solution. Okay, or you could get a solution, right? No, I mean more equations than variables. And in this case, Matthew, good question. We have three equations with two variables. Oh, I see what you're saying, Matthew. Let me thank you. So let me correct that. So here we have more equations than variables, and students will often think, well, gee, if we have more equations than variables, we have an overspecified system, and so it can't have a solution. The system would have to be inconsistent, but that's not the case, because that doesn't have to be the case. It could be the case, but it doesn't have to be the case, because you could, like in this case where we had three equations with two variables, you could have two equations that are the same. Okay, and so you have to be very careful before, on thinking on that. All right, so, now what we're going to do is we're going to investigate if our system has a solution. Are there any questions on this? Okay. No problem, Binyam, no problem. I see what I see what you mean, Binyam, no problem. Right, well, and we don't have an over specified system here. In the little example we did. So, yeah, well, Matthew, I'm saying there is for this little system here that I made, we do have a solution. We do have a solution. X1 equals 1, X2 equals 1. But generally, when students see more equations than unknowns, they think there can't be a solution possible. And usually they're right, but it doesn't have to be that way. So let's go ahead. Let's go ahead. Yes, that's right, Biniam. That's right. So let's go ahead now. So Matthew, they could be right, they could be wrong. But I'm just saying you can't say that the system's going to be inconsistent, because it could be consistent, but usually it's inconsistent. And like for our system here, what I do is I set up my three equations here. I set up my three equations, and I'm going to try to solve the system. I'm going to try to solve the system. Okay, so let me give you a moment to, and I do, you know, standard row operations, easy. All right, so let me give you a moment to copy down the row operations. The last term is 21 halves. Yes, this is 21 halves. Yep. Okay, give you a moment to copy here. Let's see. Okay, Matthew's good. Okay. Okay, that's right, Biniam. That's right. So the row operations on our system get us down to this augmented matrix here. Okay, this augmented matrix. And I have a little bit more to go on this. May I go to the next page? Or do you need a little more time to copy? Okay. We go to the next page. Here we are. Here's our, you know, our augmented matrix. And here, the last equation is 0x1 plus 0x2 equals 21 halves. That has no solution. So the system AX equals B is inconsistent, and there's no solution vector X. But what we want to do is we want to look at this geometrically. We want to look at this situation geometrically. Okay, and so what I've done here is I've written down AX equals B, and I note that A is a 3 by 2 matrix. The vector X is a 2 by 1 matrix, and of course the matrix B is a 3 by 1. Okay, and remember, you can write the matrix A times the vector X. Well, you can express that as a linear combination of the column vectors of A. So the matrix A times the vector X is a linear combination of the column vectors of the matrix A. So x1 times the column vector A1 and x2 times the column vector A2. And so that gets you down here. So what we did was we expressed this matrix equation as a vector equation. Okay. We express the matrix equation as a vector equation. And we know that this vector equation here, x1 times the vector 4, 0, 1, that's the first column vector of the matrix A, plus x2 times the vector 0, 2, 1, that's the second column vector of the matrix A. We're setting that equal to 2, 0, 1. And we know that there isn't a solution, right? We know there's not a solution x1, x2. But let's just pretend that we didn't know that. Okay, let's just sort of pretend. Well, I want to be a little bit careful here. I want to be a little careful. I kind of want us to pretend we know that, but yeah, let's say, yeah, we do know that. But let's look at it from a geometric perspective. So everything on this page, are we comfortable with? Everything on this page here before we move to the next page? All right. All right, and Maisha's still copying a little bit here. All right, I'll give you. Okay, very good. All right. Well, let's go ahead then and let's move to the next page then. Are there any questions at all with what you're seeing on this page? All right, so let's refresh here. We are trying to solve the system AX equals B. AX equals B, that matrix equation is equivalent to this vector equation here. So we are looking for x1 and x2 such that this vector equation holds. And I'm going to note here, a little note, the column vectors A1 and A2 are not orthogonal. They are not orthogonal, okay? Because the dot product of A1 and A2 is not equal to 0. Now here's what we're going to do. What does this mean that the x1 and x2 does not exist? In other words, there's no solution for x1 and x2. Let's look at it geometrically. What we're going to do is we're going to let W be the span of the column vectors A1, A2. Okay? So W is the column space of the matrix A. The dimension of this space W is 2. It's a two-dimensional subspace of R3 because the vectors live in R3. Since x1 and x2 don't exist, we geometrically have the situation below. Okay. So what I've done, well, let me give you a moment here. Okay, so, all right. So to understand geometrically what it means not to have a solution to a system of equations, I've rewritten the system of equations as this vector equation here. W is going to be the span of A1 and the column vectors A1 and A2 of the matrix A. So W is in the picture below, W is the column space of A. Since W is the span of two vectors, the dimension of W is equal to 2. It's going to be a plane in R3. The subspace W will be a plane in R3. And that's a subset of R3. Since x1 and x2 don't exist because the system is inconsistent, we geometrically have the situation below. And what I've done is, of course, I've drawn the column vectors of I've drawn the vectors A1 and A2 in my subspace W because the span of A1 and A2 generates the subspace W. But the vector B cannot lie in W. The vector B has to lie outside of W, the vector B. Because B, and why is that? Because B is not a linear combination. The vector B is not a linear combination of the column vectors A1 and A2. Binyam says this picture helps because of the geometric understanding of adding vectors. That's right. That's right, Binyam. If the vector B were, if the system of equations had a solution and the vector B were a linear combination of A1 and A2, then where would the vector B have to lie? If the vector B were a linear combination of the vectors A1 and A2, then where would the vector B have to be located? Would it lie outside W or inside W? That's right, Ryan. That's right, Solomon Binyam. It would lie in the subspace W. But since the vector B is not a linear combination of x1 and x, since the vector B is not a linear combination of the A1 and A2, vector B has to lie outside that subspace W in R3. Okay, so far so good. All right, are there any questions? All right, so looks like people are feeling comfortable. Okay, well, let me ask you this. Is there in this subspace W, is there a vector in subspace W, in that plane, that lies the closest to the vector B? Okay, is there a vector that lies closest to the vector B? Yeah, in other words, I'm going to draw I'm going to drop a perpendicular line down. Okay, drop a perpendicular line down. And indeed, the projection vector, man, hold on. The projection vector, and I know it's not perfectly, hold on, we'll get it. Hold on, I'm going to do this right. Let me just figure it out. Hold on. I'm doing all right. I got a mosquito in my subspace here. We might have to project him down onto the subspace, the desk subspace. That's maybe not a good analogy there, but okay. That's actually pretty funny, I think, but I never, sometimes insects, if I can, I take them outside, but mosquitoes, they're tough hombres, they're tough. You just can't do anything with them, yeah, the vector b half, that's right. This vector is the projection vector b hat, okay? So the projection vector b hat is the projection of the vector b down onto the column space of A is the vector that lies the closest, it's the vector in the column space of A, okay, that lies closest to the vector b. And we want to find that projection vector b. But can we use what we learned in section 6.3? Can we use the cool formulas that we learned in section 6.3 to find that projection vector? In other words, let me just hold on here. We know what the vector b is, and we hold on here. Hold on. Let me just bring up the ebook here. One moment. Let me just bring it up. I'm looking at Theorem 8 in section 6.3. Theorem 8 in section 6.3, but I'll bring the theorem up as well. Okay, so let me bring up that theorem. Let me bring up the ebook here. So of course in Theorem 8, instead of b hat, they have y hat as the projection vector. And instead of and they have a picture right here in figure 2, right? They have a nice picture here in figure 2. I mean, there's the projection vector. We're trying to find the projection vector, and in Theorem 8, the set of vectors u1 to up is a basis for w, orthogonal basis, and so instead of vectors u1 to up, we would have a1 and a2, right? The column vectors of the matrix A for our thing. Could we use this formula to find the projection vector b hat? Is that possible? Do the column vectors a1 and a2 meet the conditions of the theorem? Oh, Robin says no. Why, Robin? Okay. Robin says, well, Solomon pointed out that a1 and a2 are not orthogonal, and Robin agrees. a1 and a2 are not orthogonal. So what we'd have to do as Solomon pointed out, is we would have to create a orthogonal basis for I want to be a little bit careful here now. Hold on. Yes, what we'd have to do, well, if we're going to use this theorem 8, we would have to have a orthogonal basis for the span that would, I'm going to say this right, we would need an orthogonal basis for that subspace W for the column space of the matrix A. Okay, and we could do that. However, in section 6.5, you're going to learn that we can actually get a projection vector without having we can find the projection of one vector onto a subspace where the subspace is the span of vectors, but the vectors don't have to necessarily be orthogonal. You're going to learn a more general approach to finding a projection vector. Because sometimes, the Gram-Schmidt process, how many notice it can take time to create an orthogonal basis? I mean, sure, 2 vectors, it isn't too hard, but how many notice with 3 and 4 vectors, it takes some time? Yeah, it can be very time consuming. And so, on the exam now, I'm going to want you to show me the work on that, right? I need to see you understand the concepts, right? But you appreciate that it takes time. So let me go into section 6.5 and talk about a theorem, theorem 13. Okay. So on that note, let me get 6.5 up here and bring up theorem 13. Okay. Okay, now let me go ahead and share again. Okay, so theorem 13 here. One moment. Theorem 13, well, I want to be a little bit careful. Let me actually, before getting to theorem 13, let's look at figure 1, because figure 1 relates to what we just looked at. So they have here in figure 1, okay, hold on. This is in section 6.5. In figure 1, they have a column space of A, just like we had. Okay, column space of A, and they have a vector B outside the column space of A, and they've drawn some vectors in the column space of A. So A times x1, A times x2. Okay, what A times x1, what is that? Well, that is just A times x1 can be also thought of as a linear combination of the column vectors of A. Okay, where the weights are come from the vector x1. Ax2 is another linear combination of the column vectors of the matrix A. Okay, and that's gonna be some other vector located in the column space of A. But the vector we want is A times x hat. A times x hat, the vector x hat, are the weights, in our case, x1, x2 weights for our problem, but they are the weights that give us a projection vector. Okay, and that projection vector, which is equal to A times x hat, would be what we're looking for. Okay, and the vector x hat is what's called a least squares solution. X hat is a least squares solution. Because why is that? Well, let me go back a little bit here. A least squares, this is a definition from section 6.5, a least squares solution is a solution x hat such that the difference between the vector b and ax hat is smaller than the difference of the vector b and any other ax. Okay, so ax hat is actually the projection of the vector b on to your column space of A. Okay, and ax hat is going to equal that vector b hat, which is again the projection of b onto the column space of A. But this is why we call x hat a least squares solution. Okay, because it's the A times x hat, that vector is located in the column space of A, but it's the least distance from that vector b, which is outside the column space of A. Okay, and let me see here. Hold on. There was a question, I think. One moment. Okay, Binyam says, so when you have an inconsistent system, yes, when you have an inconsistent system, the best you can do is find a least squares solution. You can't find an exact solution of an inconsistent system, but you can find the best, but you can find a least squares solution, and that's the best you can do. Okay, so that's what we're doing. But the question is now, very good comment, Binyam. The question now is, how do we find the least squares solution? Okay, how do we find that? Because we cannot get this projection vector. We cannot get this projection vector b hat by what you learned in section 6.3, because we're not assuming that the column vectors of the matrix A are orthogonal. So we need a more general approach to get that projection vector. And here's what we do. Here's what we do. We note that if we were to take the difference between the vector b and the projection vector ax hat, okay, we note that, hold on here, we note that the vector b minus ax hat is orthogonal to every column vector of the matrix A, because the column vectors of the matrix A lie in the column space of A. So if A sub j is any column of the matrix A, the dot product of A sub j with the vector, the dot product of the vector aj with the vector b minus ax hat would equal 0, because those vectors are orthogonal. And that's true for every column vector of the matrix A. Now, if the dot product between aj, vector aj, and vector b minus ax hat equals 0, that's equivalent to saying then that the transpose of the vector aj times the vector b minus ax hat equals 0. That's equivalent. But since this is true for every vector, every column vector aj of the matrix A, we can collectively say that the transpose of the matrix A times the vector b minus ax hat would equal the 0 vector. Okay, that equation follows from theorem 3 in section 6.1. But I mean, I think intuitively, I don't think we need to go to any theorems. I mean, the fact that this is true, okay, for every vector in the column space of A, means that then this would be true. Okay, A transpose times B minus AX hat equals 0. And this is how we're going to solve our X hat, because once we get our least square solutions X hat, then we will know what the projection vector B hat is. So what we do is, since matrix multiplication is distributive, we can write this second matrix equation as this a matrix equation. But then I can say A transpose times A times X hat will equal A transpose times the vector B. And I can solve that system of equations. It's called normal system of equations, or I should say it's called the normal equations. A transpose A times X hat times, A transpose times A times X hat equals A transpose B. Those are called your normal equations. But what the book does is it just expresses that, the normal equations, with this way in equation 3, without the hat being there on the X, which I really don't, to be honest, don't quite understand. But that's how they show it. But understand, if you solve the normal equations, A transpose A times X equals A transpose B, you solve that for X, you are finding a least squares solution. Okay? And that's what theorem 13 says. Okay? And so you have a more general way of finding a least squares solution. But keep in mind, you cannot use this approach for exam 4, because exam 4, you did not learn section 6.5 yet. So for exam 4, if you see a problem from section like 6.3, you have to use the procedures you learned in 6.3. Okay, so kind of a, okay, Binyam has a question. All right, very good. Yeah, let me know if you have any questions. You understand why 3 holds, okay. Yeah, Binyam, I agree. I don't know in equation 3 why they dropped the hat off the X. I see that in equation 3. They should have really, I mean, if you look at, above, they have A transpose times A. If you look above here, hold on, let me get it here. If you look above, I'll just delete it so it makes it clear. They have A transpose times A times X hat equals A transpose times B. But then below in equation 3, they drop off the hat. And I don't really like it that they do that, because it might make you think that, hey, I can find a solution X. You can't. You're finding an X hat solution. But that's what they do. Yeah, the vector B is not equal to B hat. No. Everything's fine. Equation 3 is fine, except they drop the hat off. And they even say below that a solution of equation 3 is often denoted by X hat. So why not leave the X hat there? Why not? But at any rate, all right. So are there any questions on that? I agree. So just pretend, Binyam, the jump isn't there. All you need to know is this. Let me just see. This here. So if you want to think of A transpose A times X hat equals A transpose B as the normal equations, that's fine by me. Fine by me. All right, well, on that note now, let's go ahead and continue with this problem. Okay, let's look at it again. Okay, and again here, we're going to let A and B be the same. One moment here. We're going to let A and B be the same. And we know that the system AX equals B does not have a solution X. But what we want to do now is find the least square solution, X hat, of the system AX equals B. And then we want to determine the least squares error for our least square solution. Okay, so let me give you a moment to copy that example down before we work through it. All right, we're good? All right, so, all right. Well, so we're going to use the procedure we just learned. We're going to use the procedure we just learned here to find the least square solution. So what I did was I drew just a new picture here. It's the same, actually, it's the exact same picture that you had with the previous example, which is related to this one, right? It's the same system of equations. But I've drawn in the projection vector. And of course, b hat is the closest vector in W to the vector B. All right. And we can say that there is a solution, a least square solution, and I denote the I denote the variables. I put hats over the variables x1 and x2 to denote my least squares solution. It makes sense since the vector is, x hat. There is a least squares solution such that x1 hat times a1 plus x2 hat times a2 equals the vector b. And of course, remember, a1 and a2 are the column vectors of the matrix A. And we note also that the distance between the vector b and our projection vector b hat would be, which is a times x hat, that would be smaller than the difference between the vector b and any other ax there is. For all x in, this should be our, for all x in r squared, because the vector x is 2 by 1. Okay, so that's why we call it least squares solution. Okay, let me give you a moment to copy that. See, if I were in class, I could be kind of looking at you and seeing who's done copying and then kind of know when to move. But you can't do that here. But that's okay. We're doing all right. All right, Matthew's good. Is anybody else needing a little more time to copy here? Okay, Solomon needs a little more time. Okay. Okay, all right. Well, let's work it through. Thank you, Solomon. Let's work it through here. So from the textbook, we learned that the least squares solution x hat may be solved by solving the normal equations. And these are the normal equations here. And I put the dimensions of the matrix A and x hat and the vector B and A transpose. I put that below just so you know that the matrix multiplication is well defined. A transpose A is always going to get you a square matrix. A transpose A. Okay, and so it just comes, this is really just computational. I compute A transpose A transpose B, and then I find the inverse of A transpose A. Okay. using the standard inverse formula. It's interesting that A transpose A does have an inverse. What do you notice about the columns? I mean, here's the matrix A, right? Here's the matrix A. What do you notice about the columns, the two columns of our matrix A? Those two column vectors are, begins with two words, it begins with an L. Good. Linearly independent. That's right. Good. Good, Robin. Good, Matthew. So when your column vectors of the matrix A are linearly independent, then the A transpose A, the inverse will exist. It will exist. Now, if the column vectors of the matrix A are not linearly independent, then you can't solve the normal equations with an inverse, okay? But you can still solve the normal equations, because the normal equations is a system, it's a system of equations that you're solving, okay? And here A transpose A is invertible, but example 2 in section 6.5 will show you an example where A transpose A is not invertible. And we'll talk, we'll have a little time to mention that quickly after our Okay, so when you're ready, then I will move to the next page. We will continue our solution here. Kevin's good. All right, is anybody still copying a little bit? Need a little more time? Okay. All right, we'll wait a little bit here. Just out of curiosity, are you able to see the next page in the solution? Or do you see every page as I? All right, so you see the pages as I share them with you. Okay, all right, very good, very good. I thought that was the case, but okay, Solomon's good. All right, then let's move to the next page if we're good. Okay, hold on, Solomon. All right, no problem, no problem. Okay, very good. So now, why would we want to get A transpose A inverse? Well, the reason is, here are the normal equations. A transpose times A times X hat equals A transpose times B. And I'm going to multiply by A transpose A inverse on the left of both sides of that matrix equation. And A transpose A inverse times A transpose A gives us the identity. And so X hat equals A transpose times A inverse times A transpose times B. And I just worked out the math. I did it all by hand. But of course, in your, for your this section 6.5, there may be, I want to be a little, sometimes for when the matrices are big, you might want to use MATLAB to help you. That's okay. For section 6.5, if the matrices get kind of big, you can use MATLAB to help you. Okay, all right, let you copy this. Okay, all right, Matthew. Okay, so are there any questions? Any questions on the least square solution? Incidentally, now you want to be, just to, usually like for exam 4, I will very likely send some comments regarding exam 4, regarding maybe if there are any questions where you can use MATLAB or MATLAB's okay, I'll let you know. So you want to be checking your email, even over Thanksgiving break, right? Okay, so we're good. Can we move to the next page? All right, here we go. So the least squares error in the least squares solution is found as follows. You compute A times X hat, that's your projection vector. Then take the difference between the vector B and your projection vector. So that's that vertical distance. Whenever we drop the perpendicular, well, let me just go back here. In the picture, don't worry, I'll go back to that last page, but in the picture here, that's this distance right here. Maybe I'll put it in red. That's this distance. Okay, that's your finding. The distance between the vector B and the projection. Okay, and so here we find it. And it's going to be the square root of 84. Now, I want to mention in the book, too, they have another way to compute a least squares solution x hat. They have another way. This is the way that you really want to use the normal equations. You want to really use the normal equations. But there is a theorem 15 uses the QR factorization of a matrix, and it gives the formula to compute the least squares solution based on the QR factorization of a matrix. I'll let you look at theorem 15 on your own. They give a little proof of it. You know, the x hat would be R inverse times the transpose of Q times the vector B. That's theorem 15 in section 6.5. And they prove that. It's not hard to prove. But generally, you want to use the normal equations like we did here to find your least squares solution. Did I forget a hat somewhere, Matthew? Oh, yes, I did, right here. Thank you. Okay, here. Yep. Hat goes, hold on. Sorry. Hat right here, class. Man, I'm having trouble drawing that hat. Hold on. I'll get around this problem. How's that for ingenuity, huh? There we go. All right, and what I'd like to do, I want to just show you example 5 in the ebook. I'm sorry, not example 5. Example 5 is an example where they use a QR factorization to help you compute a least squares solution x hat. I want to look at example 2 real quick. And it'll only take me a few minutes. If you can stay, it'll be on the recording, but if you can stay a few extra minutes, that would be nice. So may I go to the, are we good here? Are there any, does anybody need a little more time to copy? Okay, all good. Solomon, are you good too? Christy's good? Maisha's good. Okay, thank you, thank you. All right, everybody's good? Okay, all right. So, all right, James, very good, thank you. All right, let me bring up the ebook here. Okay, example 2, they want you to find a least squares solution for this system of equations where A is the matrix below and B is the vector below. Now, are the column vectors of the matrix A, are they linearly independent? Or are they linearly dependent? The column vectors of the matrix A in example 2. Can one of the vectors be written as a linear combination of the other vectors? Ah, okay. That's all right. That's why I'm doing this. Can the first vector be written as a linear combination of the second, third, and fourth vectors? That's right. A1 equals A2 plus A3 plus A4. Thank you, everybody. So this means then that you cannot find the inverse of A transpose times A. Okay, you're actually going to prove that. The only way A transpose A has an inverse, as if the column vectors of the matrix A are linearly independent. You'll prove that in one of your multiple choice exercises for section 6.5. So, wait, hold on. Did I lose the book here? Hold on. Hold on, let me bring it back. Hold on, this isn't right. One moment. This is not right. Hold on, class, just give me a moment. Did my darn book disappear on me here? Hold on. Hold on, class, just give me a moment. Sorry for the delay. I'm just one moment. I might have to go out and come back in. I don't know. Let me just go out and come back in here. Thank you for your patience. Gosh. Now I got to bring it all back. Hold on. I think what happens is the book sort of, when it's open too long, the ebook, it like closes automatically. Okay, probably it wants me to pay for something, so it doesn't close. I'm getting it here. Come on, get to example 2 here. Okay, we're getting it, class. One moment. Okay, now get that thing off. Okay, let me bring it back here. Okay, so we agree that the column vectors of the matrix A are linearly dependent. How does that affect the solution? How does that affect the solution? Okay, well, let's take a look. How do you think it might affect the solution, class? How do you think it might affect the solution? Well, I'll show you. I'll show you. Seeing here, I'm getting. Okay, so they work through the normal equations. They find A transpose A, they find A transpose B. They solve the system here. And look what happens. You get a free variable in there. You get a free variable. So that's what happens. You do not get a unique least squares solution when the column vectors of the matrix A are linearly dependent. Okay? And you can geometrically think about that, why that is. But yeah. Are there any questions on that? All right, very good. Well, on that note, that's section 6.5. And once again, when you wake up tomorrow morning, exam 4 will be posted. Look for email from me, if not, either tomorrow or Thursday, hopefully later tomorrow, regarding exam 4. So exam 4 will be posted when you wake up tomorrow morning. Thank you for a very nice class, everybody, and I hope you have a nice Thanksgiving break. Okay, and 6.5, I'm gonna repost all the assignments. 6.5 will be posted too. Thank you. Have a nice Thanksgiving, Max and Ryan. Thank you. Thank you. Thank you, Bethlehem. Thank you, Kevin. Happy Thanksgiving. Thank you, Robin. Thank you, Christy. Happy Turkey Day. All right. Thank you, Solomon. Thank you, Matthew. Masha, thank you. And yes, be safe, be safe. Absolutely. Okay. Thank you, Masha. I think I'll be okay. All right, I'll stop the recording.